Log on, tune in, find out. Another good idea from Cambridge.
Now, it's my great pleasure this evening to welcome our first lecturer for the conference. This will be a lecture this evening. It's not just an after-dinner talk, but it will be a proper lecture. You can turn your chairs around to make yourself more comfortable. And we're delighted to have Lord Martin Rees here this evening. And it's not entirely a coincidence. It's partly, I have to say, intelligent in design. I can use that. But of course, it was only yesterday that it was announced that Lord Rees is the recipient of this year's Templeton Prize, and I do think we should warmly congratulate our speaker for this wonderful prize this evening. Introduction in this kind of gathering, and I won't spend very much time on that. Of course, he's been president of the Society from 2005 until just a few months ago. He's the astronomer royal, still master of Trinity College in Cambridge. And as George Ellis was reminding us at the press conference for the prize yesterday in London, has published a huge number of papers, I think about 500 papers, of which several in particular have really changed the whole fields of astrophysics and cosmology in ways of which I'm sure we're all very aware. So who better to give us our open lecture at this conference than Lord Rees.
Short understanding of the lecture. I was going to speak about half an hour. But although it's a lecture, not a sermon, I thought I would start with the text. The text will be something from an English translation of Lemaitre. He wrote, "The evolution of the universe can be likened to a display of fireworks that has just ended. Some few wisps, ashes and smoke. Standing on a well-chilled cinder, we see the fading of the suns and try to recall the vanished brilliance of the origin of the worlds." Well, Lemaître lived just long enough to learn about the modern evidence for that vanished brilliance. The background radiation, discovered in 1965, sometimes called the afterglow of creation. He also lived long enough to learn a great scientific as well as poetic truth that brings us to the stars. That each of us contains carbon, oxygen and iron atoms forged in thousands of different stars all over the Milky Way, that lived and died before our solar system formed. We are the nuclear waste and the fusion power that makes stars shine, and the cosmos is part of our environment in a more intimate way than the margin perceived. But Lemaître would have been even more elated had he been alive today to learn about current discoveries and current events, especially as they hinge on issues that would have engaged him as a Catholic philosopher as well as a scientist. And just parenthetically, I'm sure had he lived a decade longer, he would have ticked absolutely all the boxes to be an early winner of the Templeton Prize. The prize started in 1972. Well, there has been an amazing crescendo of discovery since the 1970s. And this is owed primarily to advanced instrumentation, more powerful telescopes in all wavebands, on the ground and in space, better sensors for faint radiation, and space technology. Equally important have been powerful computers, not only to analyze the data, but because we can't experiment on stars and galaxies in the real world, though we can virtual world within our computers. Those are the reasons we progressed. Armchair theorists deserve little credit. They're no wiser than Aristotle was, and they've got no further without the aid from technology. But thanks to these advances, we can now specify not only that there was a hot, dense beginning of the universe, but we can specify conditions 1 second after the Big Bang, even 1 millisecond after the Big Bang, with more confidence and precision than most of the things that geologists can tell you about the early history of the Earth. So density, composition, and the other things. But this progress in understanding the beginning of our expanding universe brings into focus some questions which Lemaitre couldn't even have proposed about what happened still earlier, in the first tiny fraction of a second, about how from amorphous beginnings in what he called the primordial atom, the cosmos evolved to its present complexities. At first sight, it seems contrary to this second law of thermodynamics that we can start off with this amorphous structure and end up with the complex cosmos of which we're a part. But essentially, they are always led by gravity, which has counterintuitive thermodynamic properties. Gravity drives things further than equilibrium. If you were to switch off the source inside the sun would deflate, contract, but we'd end up hotter in the sense of the thought. So gravitating objects have negative heat, they further to equilibrium. So the history of our universe is essentially a history of gravity causing density contrast to grow, temperature contrast to grow. So we end up starting with an almost uniform universe with our present universe where we have the blazing surface of stars, the hotter centers, and the cold night sky 3 degrees above absolute zero. Well, to get from the amorphous Big Bang to the present required a series of steps. First particles, protons and neutrons, first stars and galaxies, the synthesis of the periodic table in stars, required conditions about nuclear forces, and then the formation of planets around later generation stars, where one already has made the carbon, oxygen, and iron in earlier stars. And then, of course, after this has been set on at least one planet, the formation of the biosphere has led to the emergence, after 4 billion years, of rains capable of pondering their origins. This chain of events is sensitive to some cosmic numbers, key parameters, laws of physics. I wrote a book some years ago called Just 6 Numbers, identifying some of these numbers which, had they been different, would have led to a universe sterile or stillborn, rather than allowing complexity to emerge. These numbers were all imprinted in the first tiny fraction of a second, when energies and densities were so extreme that experiments can offer no direct guide to the relevant physics. We have some confidence going back to about a nanosecond. That's the time when all the particles move around with the energy that we achieved in the LHC accelerator in Geneva. At that time, everything in our observable universe would have occupied a volume about the size of our solar system. But that's not going far enough back to our first. In fact, the cover of Discover magazine, the American Popular Science magazine, 1 month, had a very nice image. It showed a circle beneath the caption, universe when it was a trillionth of a second old, actual size. And indeed, according to a popular theory, the entire volume we can see with our telescopes inflated from a hyperdense blob no bigger than that. And to understand why the universe has the ingredients it has, and why it's expanding where it is, it requires us to have physics which we have confidence in, which applies under those extreme conditions. We are as yet far from that. hope is that we will have a theory that unifies the fundamental laws which we can test in our ways, but which gives us confidence that we can talk about this very early phase with the same confidence that we can now talk about the first second. And of course, let's remember that in Lemaitre time, the first second was just as uncertain as this very, very early stage is now. So there's been immense progress in the last 20 years. Not only have we pushed back further into the past, but we've got an enlarged perspective on another question. How big is the universe? Well, we can only see a vast but finite whole. A finite number of galaxies, many billions, which you can see with the large galaxy. But that's in effect because it's a horizon, the shell around us, delineating the distance that light has travelled since the Big Bang. But that shell has no more physical significance than the circle that delineates your horizon if you're on the boat in the river ocean. You don't think that the ocean ends just beyond your horizon, and there's no more reason to think that space ends just at the limit of what we can see. Indeed, there is good reasons to suspect that there are far more galaxies beyond the horizon. The best argument is that if we look as far as we can in that direction and the opposite direction, then the conditions are different by less than 1 part in 100,000. The temperature of radiation is almost exactly the same. And that suggests that if we're part of some vast structure, and because the gradient is so gentle, it must go on a lot further. And that's just a minimum. It could go far, far further still. Rather just a few thousand times further, it could go a zillion times further. And if it stretched far enough, then, of course, all combinatorial possibilities would be repeated. They would be far beyond the horizon, replicas of this room. But they are far, far beyond the horizon. They make nonetheless. So, volume of space-time within range of our telescopes, what astronomers have traditionally called the universe, could be only a tiny fraction of the aftermath of our Big Bang. But that's not all. Our Big Bang may not be the only one. There are various ideas which suggest this. Again, speculative, but based on serious ideas about planetary physics. One idea is that there could be other space-times alongside ours. Rather as if you imagine a whole lot of bugs crawling around on a sheet of paper, their two-dimensional universe, they may be unaware of another population of bugs on a parallel sheet of paper. Likewise, one dimension up, there could be another universe which could be just that far away from ours, and if that distance is measured in some fourth spatial dimension, we're imprisoned in R3, then you wouldn't know. That's one possibility. Another idea is what goes by the name of internal inflation. The main advocate here is Andrei Linde, who quotes a Russian cosmologist now at Stanford. It's in a sense a much grander version of the old steady state theory. The idea is that big bangs are continually popping off within some expanding substratum, but the scale of this is happening, instead of being small, is much, much bigger than the volume we can actually see. So, it remains a possibility that what we traditionally call the universe could be just one patch of space-time in a vast cosmic archipelago. And the challenge of 21st century physics is to decide these questions, to decide whether there have been many big bangs rather than just one. And the second question that arises, if there are many, are they all governed by different physics or the same physics? Could it be that what we call the laws and constants of physics, which are the same in the lab as on the most distant galaxy you can see, maybe in its grand perspective, those laws are just, as it were, parochial bylaws in our cosmic patch. Many theories suspect this. If so, if the Big Bang might were a ring of changes, and it would then occasion no surprise that there was one one could plan fine-tuned enough to allow the chain of events against the emergence of gravity. That's one possibility. We don't know how to plan out. This is a scientific question, but a speculative scientific question. And I think there's an analogy here, if we go back 400 years. 400 years ago, Kepler thought the Earth was unique, and its orbit was a circle, related to other planetary orbits by beautiful mathematical ratios of atomic solids. We now realize that there are zillions of stars, each with planetary systems. The Earth's orbit is special, only insofar as it's in the range of radii eccentricities compatible with light, where water exists neither always frozen nor boiling. And we no longer expect a huge mathematical formula for the Earth's orbit. We think it's an environmental accident that has those particular properties. And maybe we're due for an analogous conceptual shift on a far grander scale. Maybe our Big Bang wasn't unique anymore than planetary systems. And its parameters, what we normally call the laws of physics, the latest strengths of the nuclear, electromagnetic, and gravitational forces, may be environmental accidents of how we just cool down, like the details of the Earth. Will there be a theory that tells us this? We're still groping for it. In the fashion of ancient cartographers, we will still describe here be dragons. And there are questions that we can't even yet formulate. These are Rumsfeld's famous unknown unknowns. What a pity he didn't stick to philosophy. But I think it's important that even though these other domains, other space-times, may not be directly observable, they could still be things for which we develop strong evidence. Because we don't need to be able to test all the consequences of the theory. For a theory to take it seriously, you have to be able to test a lot of those consequences. And you then take seriously other consequences you can't. To give a simple example, Einstein's theory of relativity is taken seriously because it's been tested in many contexts in astronomy, and we therefore believe what it says about the inside of a black hole, even though we can't observe it. Likewise, if we had a theory which pertained to these very high energies, which gave us insight into the forces, why the 3,000 neutrinos with a certain mass, etc., then it would be clear that theory had something in it. If it, for instance, had the properties that led to Linde's eternal inflation, we would have to take that theory seriously in the same way as now we take seriously what the universe provides. Well, will we ever have such a theory? Einstein famously averred that the most incomprehensible thing about the universe is that it is comprehensible. And I think he was right to be astonished. Because our minds haven't changed very much since those of our remote ancestors who lived on the African savannah 100,000 years ago. Our minds evolved to cope with everyday life. And it's remarkable that they have been able to comprehend the micro-world of atoms and the vastness of the cosmos. It's contingency that we've been able to get so far. But nonetheless, some aspects of reality, the unified theory of physics, etc., might elude us simply because they're beyond human brains, just as surely as Einstein's ideas would baffle a chimpanzee. There's no reason, it seems to me, why the deepest laws of nature should be matched to the level that our particular state of evolution knows. I wanted to say a bit about fundamental physical theory, what's sometimes called the final theory, unified theory, and sometimes theory of everything. The term theory of everything, I think, is both hubristic and misleading. This theory denotes a unification of the fundamental forces of nature. If it's achieved as the great intellectual achievement, it will be the end of a quest that started with Newton, who showed that the force that makes the apple fall in the same closed band orbits, continued with Maxwell, Faraday, and etc. theory is relevant to most scientists. Very few scientists are held up in their work by uncertainty about the subnuclear world or uncertainty about the bedrock nature of space and time. 99% of scientists focus on trying to understand complex processes whose underlying microphysics is well understood. And I want to say a word about the limited extent to which reductionism is relevant. The sciences are sometimes likened to the different levels of a tall building. Particle physics on the ground floor, then the rest of physics, then chemistry, and so far all the way up to psychology and the economists in the penthouse. We've got furthest to fall. And there's a corresponding hierarchy of complexity. Atoms, molecules, cells, organisms, and so forth. But the analogy of the building is appalling. In a building, insecure foundations impel everything above. But the higher level sciences dealing with complex systems aren't impelled by insecure base, because they have their own autonomous concepts and theories. Let's take a simple example, fluid mechanics. To understand why flows go turbulent and why waves break, you treat fluid as a continuum. You don't care that it's H2O. Indeed, you could solve Schrodinger's equation for every atom of turbulent fluid. You could, in principle, it wouldn't offer any insight into turbulence. The key concept is different. The mass of chaos, Eigenbaum's number, is a discovery quite disjointed from anything in the quantum or subatomic world. And moving up in the hierarchy, an albatross predictably returns to its nest after wandering 10,000 miles in the Southern Ocean. But that's not the same kind of prediction as astronomers look at celestial orbits of eclipses. And that kind of prediction could not be made even in principle by solving Schrodinger's equation. It's not a closed system. So problems in biology and in environmental and human sciences remain unsolved because scientists have yet to elucidate the patterns, structures, and interconnections. Not because we don't understand subatomic physics well. But it's important to realize that these problems of complexity are hard. The everyday world is harder to understand than atoms or stars. A simple insect is far more complicated than a star, and the fact that everyday questions like diet and childcare are issues where the scientists are less certain than anywhere else doesn't reflect the competence of those scientists. It reflects the fact that those are very complicated issues, far more complicated than anything in the inanimate world. Having mentioned life as the most complex thing in the universe, this leads to another question. Is there life already out there somewhere in the universe? Perhaps advanced life with the problems of string theory are adopted. But we don't know. But we have learned something that's relevant to this question, and it makes the night sky far more interesting than it was before. Far more interesting indeed than it was in the Lemaitre time. We've learned that many stars, perhaps even most, are orbited by residues of planets, just like the Sun is. Most of these planets aren't directly detected, but they're inferred in two different ways. The main evidence until a year or so ago came from detecting not from the planet, but from the wobble in the star. If a planet is orbiting a star, then star and planet both orbit around the barycenter, the centre of mass, the star in a smaller circle than the planet. But very precise Doppler measurements can detect motions of a few meters per second in the stars. And in this way, hundreds of planets have been discovered around other stars, but mainly giant planets, objects the size of Saturn or Jupiter as well as unfortunately, to detect an Earth-like planetary technique requires detecting a motion of only a few centimeters per second in the centre of a star, and that's too small to be detected by these spectroscopic methods. But of course, we'd be especially interested impossible twins of our Earth. Planets the same size as ours, orbiting on the sun and other stars, at distances the sun, such that water can exist. And this is a greater challenge than the giant. And so far, we have only indirect evidence by, as it were, detecting the shadows. And the big breakthrough here, which is really ongoing, comes from the NASA Kepler spacecraft, which was launched just 2 years ago. What this is doing is pointing at an area of sky about 7 degrees across and measuring the brightness of 150,000 stars in that field of view. Measuring the brightness of each of those stars to a precision better than 1 part in 10,000, and doing the same thing every half hour. We've been doing it for 2 years, and going another 3. And what it is trying to do is to detect the slight dimmings in the star if a planet transited across in front of it. For instance, if the Earth transited in front of the Sun, and you were looking at this huge distance, you would see the Sun get dimmer by 1 part in 10,000. The Earth's diameter is about 1% of the Sun, so the area covered is 1 part in 10,000. And the hope will be that Kepler will discover many Earth-like planets this year. It's already found evidence for about 1,000, but these are mainly on closely orbit. It's obviously it's only about 2 years, and you've got to observe 3 passages before we're sure it's beyond orbit. So we have to wait a couple of years before we can find out how many Earth-like planets there are for the system. But seeing the shadows of these Earth-like planets isn't enough. We'd like to actually image them, and that's hard. To realise just how hard, let's suppose an alien astronomer with a powerful telescope was looking at our Earth and our solar system from, say, 50 light years away, just in the right side. Well, our planet would seem, in Carl Sagan's nice phrase, a pale blue dot, very close to its star, our Sun, which outshines it by many billions. Far, far next to us. Very hard to detect. But if you could detect it, then you could learn something about it. These aliens, looking at the pale blue dot from 50 light years away, would find that the shade of blue would be slightly different, depending on whether the Pacific Ocean or the landmass of Eurasia was facing it. So they could infer the length of our day, the seasons, that there were oceans and continents, even whether the water in those oceans was rough or smooth, the gross topography, and the climate. By analysing the faint light, they could infer perhaps it had a biosphere or uncomfortable beings. Well, that's what the aliens could do with a powerful telescope, looking at us 50 light years away, and in 20 years' time, that's the kind of thing we'll have the telescopes to start to do for putative Earth-like planets around our stars. And this will be a really exciting development. Well, will there be life on any of these planets? We still know too little to say whether alien life is likely or not. Essentially because the origin of life here on Earth is still an unsolved big problem. A fascinating one, surely, to the most earthbound biologists, and something that might be understood more clearly. If we understood the origin of life on Earth, we'd have a better idea how likely it was to have started elsewhere and in water. And of course, we sort of stick attention when we look for evidence of life to Earth-like planets, because we mustn't be too anthropocentric. Sometimes people tend to feel that you've got a planet just like the Earth. This book called Rare Earth said that the Earth is very special and that we could get life under those conditions. But I think that's a fallacious argument. It's rather like saying, isn't it amazing that our legs are just long enough to reach the ground? It's not really at all. So I think we ought to be open-minded about whether a life could form under different environments. And science fiction writers have had other ideas. The blue-like creatures floating in the dense atmospheres of Jupiter-like planets, Incidentally, I tell my students sometimes that it's better to read first-grade science fiction than second-grade science. It's more entertaining and perhaps no more likely to be wrong. Well, even if simple life turned out to be common, it would then be a separate question whether it would be likely to evolve into anything we might recognise as intelligent or complex. But of course, as people here know, there are searches, the so-called SETI program, to look for artificial signals. This is a fascinating quest. I wrote on my breath of success. They're looking for a string of prime numbers or digits of pi or something like that. And of course, if they succeed, then it would be remarkable. It would show that concepts of logic and physics, if not consciousness, existed elsewhere than in the hardware in our skulls. That would be remarkable. And it's not at all clear that they will succeed. Although I would not rule out completely in this room that people are looking. Of course, as a strong law, I often get letters that people think they know that there is intelligent life, and even physically here. I tend to be sceptical on the grounds that if aliens have made an effort to come here, would they have just met a few well-known pranks, made a few corn servants and went on the way? So I tend to get these people to write to each other. And if you do that, you sometimes find that they get on well with each other, or you can get a letter back weeks and say, why did you tell me to write to that nutcase? Well, if the SETI searches do succeed, we then realise we've been one in a huge number of views of intelligent beings. And let's not forget that this was not a surprise people in the past, in the 20th century. In fact, I remember a Lemaitre Conference, George Gordon and others had written. And indeed, I'd like to quote something else from Thomas Wright of Durham, who was a sort of mystic and scientist in the 18th century. And he said the following, very nice quotation. In the great celestial creation, catastrophe of a world such as ours, or even the total dissolution of a system of worlds, may be no more to the great author of nature than the most common accident of life with us. And in all probability, such final and general doomsdays may be as frequent in the cosmos as even birthdays or mortality with us on the earth. Well, that may be the case. On the other hand, perhaps E.T. doesn't exist. Earth's intricate biosphere couldn't be new. And that may be disappointing to the searchers, but it would of course have its upside, because it would entitle us to be less cosmically modest. Our tiny planet would then be the most important place in the galaxy, perhaps even a seed from which life could spread through the entire galaxy. Finally, I'd like to focus back closer to the here and now. I'm often asked, is there a special perspective that astronomers can offer to philosophy and our general view of our place in nature? Thomas Wright thought so. Let me quote something else from him. He said, I can never look upon the stars without wondering why the whole world has not become astronomers, and reconcile them to all those little difficulties incident to human nature without the least anxiety. Well, this sort of serene unconcern doesn't reflect my attitude, nor is it my impression that my colleagues in cosmology are any more serene and relaxed about the everyday world. We fret just as much about tomorrow, next week, and next year. But I do think that although our subject may make us serene, it does give us one special perspective. We do our own planet, obviously, in the vast context. But more importantly, we're mindful of the immense future that lies ahead. The stupendous time spans of the evolutionary past are now part of the culture. Maybe not in parts of Kansas, etc., but certainly in most places. Our present biosphere, you know, is the outcome of more than 4 billion years of evolution. But most people, they're familiar with that, still somehow think we humans are necessarily the culmination of the evolutionary tree. And that can surely hardly seem credible to any astronomer. Our sun indeed formed 4.5 billion years ago, but it's got 6 billion more before the fuel runs out, and it flares up, engulfing all the planets. And the expanding universe will continue, perhaps forever, destined to become, according to the best long-range forecast, ever colder, ever empty. Put to the island, eternity is very long, especially towards the end. So, any creature witnessing the sun's demise 6 billion years hence would be human. They're as different from us as we are from above. Post-human evolution here on Earth and perhaps beyond could be as prolonged as the Darwinian evolution has led to us, and even more wonderful. Darwin himself realized this. He said, some of his works, that no species would preserve its unaltered likeness into distant futurity. And of course, we can now strengthen that statement, which is clear that future evolution won't be on the slow timescale of natural selection. It will be, for good or ill, on a much shorter timescale, allowed by technology, genetic modification, etc. So all the more reason to suspect huge developments in post-human evolution in the years ahead, in the millennia and billions of years. But even in this concertina timeline, extending billions of years into the future and later into the past, this century may be a defining moment. It's the first in our planet's history, 45 billion centuries so far, when one species, namely ours, has Earth's future in its hands and could jeopardize life's immense potential. Potential which could extend for billions of years. So, my final thought is that this peregrine dot of the cosmos is a special place. It may be a unique place, and we're its stewards at a especially crucial era. And that's a message for us all, whether we're astronomers or not. Thank you.